So hello everyone, in this video we'll be solving another LeetCode problem and the problem name is largest magic square. So a k cross k magic square is a k cross k grid filled with integers such that every row sum, every column sum and both the diagonal sum all are equal. The integers in the magic square do not have to be distinct and every 1 cross 1 grid is magic square by default. In the end, they are saying that given a m cross n integer grid, return the side length k of the largest magic square that can be found within this grid. So what the question is saying that you are given some grid. Let's say this is the grid, and in this you need to find the largest magic square grid. Now what is a magic square grid? It is a grid. Let's say this is the square grid we are taking. So it is a grid such that it's every row sum, it's every column sum, as well as the sum of the diagonal and sum of the anti-diagonals all are equal. And then we need to return the largest magic square grid. So this is a 3 cross 3 grid. Now it can happen that we can get a 4 cross 4 grid as well, which satisfy the condition. So we need to return 4 cross 4 grid, or basically we just need to return 4, the side of the square. So this is what the problem is saying. So it is pretty much easy to understand, and the constraints of this problem are very low. I think it is around 50 only on m, n value. So even the brute force way will work very easily. So first we will discuss the brute force way and then we will see the optimized approach. So what is the brute force manner? So let me just draw the grid. So let's say this is the grid that you have. So you can, in the brute force way, you can check for each and every k value. K is nothing but side of the square or the magic square if it is possible. So you can check on for each and every side starting from each and every index. So you can check for creating a side of, let's say, 3 cross 3 from here, this I comma j value. Then you can do the same for starting with I comma j value here. So your magic square will be something like this, or your square will be like this. Then you can check for this value. Then if you are standing here, you can check for this particular square. So on and so forth, you can check for each and every square. Inside each and every square, you will compute all of the rows sum. So let's say you are checking for this square, this 3 cross 3. So first you can compute the first row sum, then second row sum, then third row sum, then you can compute the first column sum, then you can compute second column sum, and then you can compute third column sum. Then you can compute the diagonal sum, and then you can compute the anti-diagonal sum. In the end, if all of the conditions are matching, if all the conditions are satisfied, then you can say that, okay, this is the magic square grid, and it will run in the brute force way because the constraints are very low. So you can just compute each and every row sum, you can compute each and every column sum, and you can compute diagonal and anti-diagonal sum, and if all the conditions are satisfied, that means it is a magic square. So you can keep an answer, or you can just start your k value from largest possible value, and whatever is the first magic square, you can just return its side, because we need the largest value of k possible. So we can just start from the largest value k possible, and whichever is the first value which is a magic square, you can just return that k value or the side value. So this is the brute force manner, but we can optimize this. How we can optimize this? We can use prefix sums technique in order to optimize this solution. Now obviously you might have got the hint from this, seeing the question only in the brute force only, like we are computing row sum, row sum, then column sum each and every time. So why not pre-compute this value and get this answer in O of one time? So what you can do, what prefix sum technique says that, let's say this is the prefix sum. So if you want to get the sum from L to R, let's say this is L, this is R. So you can get this sum from L to R in the prefix sum. So let's say prefix sum of L to R. So you can get this by prefix sum of R. Prefix sum of R minus prefix sum of L minus 1. So you will have sum till here. you will have sum till here. Now if you subtract this sum from this entire sum, you will get the sum which is lying within this L to R range. So we will use this prefix sum techniques in the matrix part, and we will pre-compute all the row sum and column sum and just do the same thing that we are doing in the brute force manner, but we will not compute the sum. We will just check whether this prefix sum, whether this particular row sum exists or not. So that will make us our solution the row sum and column sum part in O of one time. So this is the optimization part. So let me just show you how we can do the prefix sum of row and column in this grid part. So let me just draw the grid, and then we will understand how we can do the prefix sum in the same matrix part. So yes, this is the grid, and let's say we are currently at the square, which is this part. So we are at this 3x3 square that we are checking. So for all the row sum, column sum, and diagonal and anti-diagonal, we need to check. So our j would be currently here, our I would be currently here, and our side is currently 3. So first of all, let's say we need to compute this particular row sum. So what we need to do, we need to get the sum till here, and we need to subtract the sum of this part. So if we subtract this part sum from this part, so we will get the sum of this area. So now instead of prefix sum, we will write row sum, because now we are like dividing all the things into on the basis of row and column. So row sum of what? From j till j plus side minus 1. Why j plus side minus 1? Our side is 3 and our j is here. So if we do j plus 3, it will be coming here, but we need to go till here. So it is what? Minus 1. So to get the sum from j to j plus side minus 1, it is nothing but row sum of I will remain same, because for the current row we need to get the particular sum part. And then how will we get the sum till this part? This is nothing but we need to get the sum till here. So this is nothing but j plus side minus 1. So for the ith row, we will just get this entire sum, and then we will subtract this part. So what is this part? J minus 1. So minus row sum of I comma j minus 1, and you need to additionally check whether this j is greater than 0 or not, because then only we will be able to check j minus 1, otherwise it will get out of bounds. So this is how we'll get the row sum, and similarly we will get the column sum as well. So for the column sum, we will do the same thing. So let's say if we are at currently want to compute this particular column sum. So how we can do? We can just get the column sum till here, till this part, and subtract this part. So this part is what? How we can get this part sum? This is again simple. I plus side minus 1, and this part is what? This is I minus 1. So same thing, the thing which we are doing in the row part, just switch on to the columns part. So to get the column sum from I till I plus side minus 1, what we can write? We can simply write col sum of I plus side minus 1 comma j minus col sum of I minus 1 comma j. So this is how we'll be getting the column sum part. Now let us see the sum for the diagonal and anti-diagonal. So let's say I'm just drawing that particular 3x3 grid so that it is more easier to visualize. So we'll be running a for loop to get this diagonal part. Let's say we are running a loop k, which will be from whatever the current I value and j value will be up till the end. And for each and every k value, let's say how will we get this particular diagonal sum? So let's say we are currently at j here and I here. So this is nothing but I comma j, this is nothing but I plus k comma j plus k, and this is nothing but I plus k again, j plus k, depending on what k value is during the iteration. So for diagonal sum, it is easy. We just need to run the k loop, and we just need to keep taking the sum of I plus k part and j plus k part, because this is how diagonals work. So this is I comma j, this is I plus 1 comma j plus 1, this is I plus 2 comma j plus 2. Now for the anti-diagonal part, first we need to reach here, then we can go towards the below part. So what is this position? We have already discussed. This is nothing but j plus side minus 1. So this is not the entire grid that I have drawn. I am just taking that 3x3 part from that particular grid. Now if we are at here, we can again run the same k loop, and what we need to do, we need to increment in the column side, in the row side, but we want to decrement in the column side. So what is the anti-diagonal sum? So anti-diagonal sum, it is nothing but I will go from I plus k only, because we need to increment in the row part. So we will be here first, then we will be here in the row part. But for the column part, you see, we are decrementing at each and every step. So how we are decrementing? We are decrementing from this last part. What is this last part? This is j plus side minus 1. And how much we are decrementing? This k part. So minus k. So first we will be at this position, then we will be at this particular position, and then we will be at this particular position. And in the end we can just keep a check, or not in the end, we can side by side, after checking the row sum and column sum, we can check whether all row sum are equal, whether all column sum are equal or not. If there was anywhere in between the sum was not matching, we can just break from that particular part, and there is no need to check the other things. But after in the end everything, all the condition matches, we can just return that particular k value. So yes, this is the code. So first I have declared integer n and m, which is nothing but n cross m grid. So in the question they have given m cross n, but I usually prefer to take n cross m. There is nothing much change. I have just changed the variable names. So n is the number of rows, m is the number of columns. Then I have declared two vectors of again size n cross m, which will take care of the row sum and the column sum. So first we are computing or filling the row sum part, basic prefix sum technique, and then we are filling the column sum part with the same basic prefix sum technique that we have seen in the drawing part. Now what we need to do, we need to check all particular side values. So first we can check for square of side 2 cross 2, then we can check for square of side 3 cross 3, then we can check for size square of side 4 cross 4. So what we can do, we need to return the largest square possible. So we can start iterating from the largest square possible only, and whatever is the first square which is satisfying the magic square conditions, we can just return that particular side. So we are iterating from the largest square possible. So we are checking from the largest square possible. And what can be the maximum square side? Obviously we can't go beyond n and m, and among that n and m we need to take the minimum value, because let's say the n value is 2 and the 3 is the m value. So you can't create a square of 3 cross 3. You can only create square of 2 cross 2 in this case. So that's why we are starting from the minimum of n comma n, and we are going up till 2, because 1 cross 1 is always a magic square grid. So if we don't get an answer, we can simply return 1 in the end. So for each and every square, we are trying to make square for each and every cell. So what I'm saying, so let's say this is the grid. So let's say currently our side value is let's say 2. So what we can do, first we can start from here, and we can try to create a magic square or square from this particular position. So this is how a 2 cross 2 square will be formed. Then we can try out making a square from this particular position or this particular cell. Then we can try out from this particular cell. So this is what we are doing. For each and every I comma j value, we are trying to create a square of side cross side. So this is what we are doing. So we are going on to each and every cell, and we are trying to create a square. So we need to be within the range, because starting from here we cannot create a square, it will go out of bound. So we need to check that also. So our I part and j part must be within the range. And for each and every square that we are creating, let's say we have created this particular square. Now we need to check whether this square is a magic square or not. So I have written a function which checks whether this particular square is a magic square or not. If it is the magic square, we got the largest square or the largest magic square. So we can just return its particular side. This side is nothing but this particular value. If it is not, we can continue our iteration to find the first magic square. And whatever is the first magic square we get, we can simply return its side. In the end, if we did not get any particular magic square of this side, no worries. The 1 cross 1 is always a magic square. So in the end, we can just return 1. Now we can check what we are writing in this magic square function. So let us check that now. So this is the is magic square function. So first of all, we have passing the current I value, current j value, the side, the row sum, column sum, and the grid. So we have already computed the row sum and column sum. Now we need to check whether all particular row sum. So let's say this is the 3x3 grid or 3x3 square which we are currently checking. So first we need to check whether all rows have the same sum, then we will check all columns have the same sum, then we will check all this diagonal and anti-diagonal have the same sum or not. So this is what we are checking in this particular function. So first we need to check what we need to have the target sum. So we can always take this first row sum as the target sum. So all of the rows sum should be matching to this target sum, and all of the column sum should match this target sum, and both the diagonals and anti-diagonal should match their sum with this target sum. So we are taking the first row sum as the base sum. So we can take target sum with the first row sum. Obviously we have seen how we are taking we are getting the sum from the prefix sum technique. So the same thing, I comma j plus side minus 1. So let's say this is the grid, this is the grid. So you want to get the sum in this part, in this particular part. So you will take this sum, entire sum, and you will subtract this sum. So this is what we are doing. So we are getting the entire sum from j plus side minus 1, and we are subtracting j minus 1 part, if and only if our j is greater than 0. So we need to check this condition. Then we got a target sum, so we can keep a flag variable which is true, which will check whether till now our conditions are matching or not. If the condition are not matching, we can simply set it false and we can return false from here. So now what we are doing, we have already taken this first row sum as the base sum. Now we are iterating from on the each and every row, and we are again computing this sum for each and every row, and we are checking whether this current row sum is equal to the target sum or not, whether this current row sum is equal to target sum or not. So if it is equal, then continue your iteration, but if it is not equal, set this flag value to false and break from here. In the end, you can check after this checking row sum part, your flag is true or not. If it is true, that means all the row sum are equal to the target sum. So continue and check for the column sum and the diagonal sum. But if it is false, that means you're in the row part only your sums are not matching, so no need to check further. So simply return false from here. Then we are checking for the column part if the flag remains true. So same thing we are doing. So in the row part, what we were doing, we were taking each and every row sum. Now we are checking each and every column sum like this. So again, how we can check this column sum part? So let's say this is the grid. So let's say you need to get this particular column sum. So we will compute sum till here and subtract this particular column from here. So we will get this particular column sum. So same thing we are doing here. So I plus side minus 1 and I minus 1 we are subtracting, if and only if this I is greater than 0. In the end, if this current column sum is not equal to target sum, return or set your flag to be false and break from here. Same condition checking we are here also. Then we are checking for the diagonal and anti-diagonal. Now for the diagonal, we have seen we need to run a k loop to get the like what you can say the diagonal to like iterate over all the diagonals. So first we will be here, then we will be here, then we will be here. So we can iterate with the help of k. So we need to increment in the row part and the column part. So we are just for the diagonal part incrementing with the help of I plus k and j plus k. For the anti-diagonal part, we need to start from here. So first we are setting our j pointer to here. So you can see our j is side j plus, our j is what, j plus side minus 1, or rather what you can say, the column is what, j plus side minus 1. Now from here we need to increment in the row part but decrement in the column part. So we are incrementing in the row part like plus k, and we are decrementing in the column part with minus k. In the end, if the diagonal sum is not equal to target or anti-diagonal sum is not equal to target, simply return false. And if all the conditions are matching, that means your row sums are equal, your column sums are equal, and your diagonal and anti-diagonal sums are also equal. So simply return true. So this is what we are doing in this entire code. I think it is easier to understand. Even the brute force solution was working in this particular example, and even the optimized solution is very easy if you know prefix sum technique. So I hope you understand this solution. Thank you for watching.